Lesson on rotation. Whenever you see an object rotating, that rotation is produced by a torque. Torque produces rotation. And how is that torque applied? Well, by a force at a distance from a pivot point. Let's take a look at two examples with this bowling pin here. How does a bowling pin move if I apply a force to the bowling pin directly through its center of mass? Then the bowling pin will slide right along the lane. How do you think the bowling pin will behave if I apply a force here? That is, I apply the force a certain distance away from the pivot point L of that bowling pin. If you said the bowling pin will fall over, then you're correct. But how exactly does it fall over? Let's observe this bowling pin here on the right, falling over. So notice the bowling pin started here as it was upright, and then it fell over. Well, the bowling pin actually rotated as it fell over. This rotation is due to a torque. We could calculate that torque if we knew the force applied multiplied by the lever arm L. Force is measured in newtons. The lever arm would be measured in meters, and thus the units for torque are Newton meters. You apply torques every day when you open a door. Every door requires a certain amount of torque to be opened. That torque would depend on the different physical characteristics of the door, its mass, its size, etc. Apply a force right here at the doorknob and push the door open. That force you apply is also a certain distance away from the hinge. The hinge would be considered the pivot point, and the lever arm would be measured from the hinge to where you apply the force. Here you apply the force at a distance away from the hinge, and that door would actually rotate to be opened, as seen here on the right. You would apply a force here at the end of the door, a certain distance away from the hinge, which we would call that lever arm, and as a result, the door is going to rotate to open. Let me ask you a question. How much force do you think you would need to apply if you pushed through the center of the door to open it? Well, if you guessed more force would be necessary, you'd be correct. Because to create the same amount of torque, if you decrease your lever arm distance to half the distance, then it would take twice the amount of force to get that door open. Balance torques. Here we have a meter stick on a fulcrum. What do you think will happen if I place this 2 kilogram mass a distance of 20 centimeters away from the fulcrum? Well, this meter stick would then rotate. And we can observe that rotation would be counterclockwise. So what would I need to do on the other side of the meter stick over here to balance that out? Well, if I had a 1 kilogram mass, I would have to put that 1 kilogram mass at twice the distance away from the fulcrum to be able to balance the torque from this 2 kilogram mass. So we have a 2 kilogram mass, a distance of 0.2 meters away from the fulcrum, balancing out by a 1 kilogram mass at twice that distance, or 0.4 meters away from the fulcrum. 2 kilograms at a distance, 1 kilogram would be at twice the distance to balance it out. Let's show how those torques are balanced. That is, the torque on the left of the meter stick from the 2 kilogram mass will balance the torque on the right of the meter stick by the 1 kilogram mass. For these torques to be equal, the force on the left times the lever arm on the left will have to equal the force on the right times the lever arm on the right. The forces the masses exert on the meter stick are their force of gravity, which is just mg. The force on the left would be the mass times g on the left times that lever arm. The force on the right would be mg times the lever arm on the right. So the torque on the left would be the 2 kilogram mass times g, or 9.8 meters per second squared, times the lever arm on the left. This results in a torque on the left of 3.92 Newton meters. So let's see if the torque on the right equals that. We take 1 kilogram times 9.8 meters per second squared times 0.4. And we see we also get 3.92 Newton meters. Thus, the torques are balanced, and there is no net rotation. Rotational inertia. Newton's first law for rotation states an object rotating will stay rotating until acted upon by an outside torque. Remember, torque produces rotation. This rotational inertia is an object's resistance to rotating. Just as inertia was an object's resistance to changing its states of motion, rotational inertia is an object's resistance to rotating. This rotational inertia depends on mass, just like inertia does, but in addition, it depends on where the mass is located. Rotational inertia is the letter capital I, and it's proportional to mass and where the mass is located, or the radius squared. A great example of this is a figure skater performing a scratch spin. As she enters the spin, her arms are far apart. Thus, her mass is located much further away from her rotational axis, which would be straight through her body here. With this larger axis of rotation, we would say she would have a large rotational inertia, meaning it would be more difficult for her to rotate, and she would rotate more slowly in this position. When she brings her arms in, she reduces her radius of rotation. It's much smaller, and thus she reduces her rotational inertia to a smaller amount. This makes it easier for her to rotate, and she will rotate faster. Just as we have linear momentum, we also have angular momentum. Let's recall linear momentum symbolized by the small letter p, and that depends on mass and velocity. Angular momentum depends on similar things. Angular momentum is represented by the capital letter L and depends on rotational mass, which we call rotational inertia, and our angular speed, represented by this Greek letter omega, which is a curly W. So angular momentum is the rotational counterpart of linear momentum, where linear momentum depends on inertia and speed, angular momentum depends on rotational inertia and angular speed. Linear momentum, angular momentum is also conserved. That is, the initial angular momentum must equal the final angular momentum at some time later. Let's take a look at our figure skater again. Recall, with her arms apart, she has a large rotational inertia and spins more slowly. We will say now that she has a small angular speed. Now when she brings her arms in, that reduces her rotational inertia, and she can spin faster. That is, she'll have a larger angular speed. Why exactly does she speed up or increase her angular speed when she reduces her rotational inertia? Well, the conservation of angular momentum tells us why. That is, her angular momentum before the spin must equal the angular momentum after the spin. This initial angular momentum, based on a large rotational inertia and a small angular speed, has to equal the final angular momentum. So if we decrease the rotational inertia, the angular speed has to increase to conserve angular momentum. We will apply these concepts of torque, rotational inertia, and angular momentum to different demonstrations in class this week. Thank you for watching, and see you in class.